In the last class, we started looking at how to plot Bode plots, isn't it? So Bode plots are nothing but what? Bode plots are nothing but how the amplitude ratio varies with frequency and the phase angle varies with it. That is what we have seen in the last class. Correct? These are the Bode plots which we have seen in the last class. And towards the end, we said we are going to look at another way of representing the frequency response. Why these two students are sitting at the back side? Are you from this class? नहीं, अगर आपको ये सुनना है तो बैठ सकते हो. You are welcome. So now what we are going to look at is the another or alternate way of representing frequency response, which is referred as Nyquist plot. Okay. So in the Nyquist plot, what we do is we actually plot real part of the g of j omega versus imaginary part of g of j omega. So you can see here. So imaginary part of g of j omega is the ordinate, whereas real part of g of j omega is the abscissa, and that we are plotting in a complex plane. Now you may ask me, what is the advantage of doing this? Isn't it? There is a Bode plot. Why you are doing it one more? Why you are mathematically making our life here all the time? All these new terms are keep on coming one by one. Isn't it? So there is a reason why we are doing this. We are doing this because in Bode plot you have to show two plots together in order to get the frequency response. Correct? In this particular case, you don't require two plots. Only in one plot you can show both amplitude ratio and phase angle. How amplitude ratio is varying when omega tends to 0 and when omega is varying from 0 to infinity. How the amplitude ratio is varying and how phase angle is varying, both you can show in a single plot. That is that. Okay. Now this particular Nyquist plot is a Nyquist plot corresponding to a third order. We will again come back to it. Okay. Now how we can read this Nyquist plot? You can take any point on this Nyquist plot. Let's say a point here. This particular point is corresponding to a frequency omega 1. And if you calculate the distance of this particular point from the origin, that particular distance actually refers to an amplitude ratio. And whatever the angle this particular straight line is making with the real axis, that particular angle is a phase angle. So you can see that both amplitude ratio and phase angle, both you can show in a single plot, unlike a Bode plot where you have to show two different plots. Okay. Now you can see that here the imaginary axis is a g of j omega, imaginary part of g of j omega, and real axis is a real part of g of j omega. So now in this particular case, if I wanted to find out the distance of this particular point from the origin, what I am going to do? I am going to find out the square of the real part of g of j omega plus square of the imaginary part of the g of j omega, and if I take the under root of that, I am going to get a straight line distance between this point and the origin, isn't it? Correct? But this particular expression is nothing but what? This particular expression is the expression of amplitude ratio. So clearly this distance refers to a amplitude ratio, isn't it? Correct? Then the another thing is the phase angle. As I said, the phase angle is nothing but the angle made by this particular line with the real axis. So here the phase angle is given by tan inverse of imaginary part by real part, isn't it? So that is nothing but just a phase shift. So both phase angle and amplitude ratio you can show in a single plot. Okay. Now let's look at different systems. Remember I said this particular plot is corresponding to a third order system. Okay. I will again prove that why I am saying that this is for a third order system. So let's look at a first order system first. So first order system will have a transfer function given by Kp divided by tau ps plus 1, isn't it? Kp divided by tau ps plus 1. And what will be the amplitude ratio? Amplitude ratio will be Kp divided by under root omega square tau p square, and phase angle will be tan inverse of minus omega tau p. Correct? Now in this particular case you can see that when omega tends to 0, when omega is equal to 0, what is the amplitude ratio? When omega is 0, omega tends to 0, then amplitude ratio is 1, isn't it? And when omega tends to infinity, amplitude ratio is 0. Correct? Similarly, when omega equals to 0, what is the phase angle? Tan inverse of minus 0 is 0. And tan inverse of minus infinity is minus 90. Isn't it? So now you can see here that this particular Nyquist slot is starting from this particular point, which is a point A, where the distance of this point A from the origin is 1. So you can see that this particular point is actually corresponding to a point where omega is equal to 0. And you can see that this particular point is making an angle with a real axis which is 0. So your phase angle is actually 0 at this point. So this is the point which is corresponding to omega equals to 0. And when omega tends to infinity, my amplitude ratio is 0. Isn't it? That means when omega tends to infinity, I should meet this particular point where the distance is 0 from the origin. But you have another requirement. And what is the requirement? The phase angle should be minus 90. So phase angle should be minus 90 is what? This particular Nyquist plot should not go here as a straight line, as a horizontal line. It should go like a curved line like this, so that it should make an angle of minus 90 at the origin. It should make an angle of minus 90 at the origin. Can you see? So that is why this particular line is curved line and it is touching this particular point at 0 origin with an angle of minus 90. Now both the conditions are satisfied. Now what happens when omega equals to 1 by tau? Omega equals to 1 by tau, which is a corner point. Isn't it? Corner point. At corner point, what is the phase angle? At corner point, at corner frequency, what is the phase angle? We have already seen that. At the corner point, what is the phase angle? Minus 45. So clearly you can see in a Nyquist plot, this is the point corresponding to a corner point, isn't it? If I draw a straight line from here to connect this point, you can see that this particular point is going to make an angle of minus 45. So you can see why the shape is like this. Why I have not drawn any other shape here. There is a reason. It's not arbitrary. Okay, is it clear to everyone? Yes, no? Okay. Now let's move to another system. Okay. Let's extend our 1, isn't it? When omega tends to infinity, amplitude ratio is 0. Second order system, when omega tends to 0, amplitude ratio is again 1 for second order system. And when omega tends to infinite, what is the value of amplitude ratio? Again 0. But the real interesting fact here is a phase angle. When omega tends to 0 in a first order system, my phase angle was 0. And when omega tends to infinity, my phase angle was minus 90. But in case of a second order system, when omega tends to 0, my phase angle is 0, that's okay. But when omega tends to infinite, my phase angle is minus 180. It's not minus 90. It is minus 180. So that means what? This Nyquist plot should not be connecting here in the first quadrant. It should connect to the origin in the second quadrant. See, this is the first quadrant. So first order process, the Nyquist plot gets terminated only in the first quadrant. But in a second order system, the Nyquist plot gets terminated in the second quadrant. So you can see that this particular Nyquist plot is getting connected to origin here by making an angle of minus 180 with the real axis. That's why this Nyquist plot is coming like this and connecting here, making an angle of minus 180. Is it clear to everyone? Correct. Now there are two cases. Remember, in a second order system, in some cases your amplitude ratio goes above 1. When your frequency is less than 0.707, then you see a maxima. Isn't it? That's what we have seen and proven earlier. This is the case. Isn't it? You can see when your zeta value is less than 0.707, that we have already proven here. 0.707, in that case you see a maxima. So maximum is what? The value of amplitude ratio is going above the value of 1. Isn't it? Now in this particular case, you can see this Nyquist plot, you can see that this is the unit circle. The dotted line which I have drawn is a unit circle. Any point on this dotted line will have a distance of 1 from the origin. Isn't it? So you can see that what is the amplitude ratio in Nyquist plot? Distance from the origin. Distance from the origin is the amplitude ratio. Correct? So you can see that when your zeta value is less than 0.707, you will have some region in which your amplitude ratio is more than 1. And that is the reason why this red colored Nyquist plot is going beyond this unit circle. This Nyquist plot is going beyond the unit circle because this is the case when my zeta value is less than 0.707. Isn't it? So when my zeta value is less than 0.707, only in that case my Nyquist plot goes above the unit circle. Okay. Now let's look at when zeta value is greater than 0.707, then the Nyquist plot do not go above this unit circle, and in both the cases anyway the Nyquist plot get terminated in the second quadrant while making an angle of minus 180 with the real axis. Is it clear to everyone? Is it clear, not clear? Now the Nyquist plot going beyond the value of 1. Nyquist plot going beyond the value of 1, amplitude ratio value beyond 1 is a very important case. We will again come back to this fact. Why I am stressing more and more that in some cases it is going beyond 1. There is a reason. Okay. Okay. Now let's extend our analysis to slightly more complicated case. So far we have seen first order system, second order system. Let's say my system is a third order system. So third order system, my phase angle when omega tends to infinity should be minus 270. So that means my Nyquist plot should terminate at origin in the third quadrant. So that's what is happening. You can see this Nyquist plot is getting terminated at the third quadrant. At the third quadrant. Okay. Clear? Let's look at another case of date time. Date time. What is the transfer function of the date time e raised to the power minus TDS, isn't it? What is the amplitude ratio for the date time? 1. And what is the phase angle? Phase angle is minus omega tau d, omega t d, minus omega t, isn't it? So in this particular case, when amplitude ratio is 1, that means what? The date time will represent the unit circle. Unit circle. And you can see that even though you are starting from this particular point, as the omega increases, it is going to encircle again and again. It's not going to get terminated at the origin. So this is a slightly different type of plot you are getting here. Remember, whenever you are having first order process, second order process, third order process, your phase angle approaches to some value. But in case of date time, it continuously decreases. Monotonically it is decreasing. It is not approaching to some value. That's what you can see here. It is encircling this particular unit circle again and again as omega increases. Is it clear? Okay. Then let's look at the pure capacitive process. Pure capacitive process, the transfer function is Kp divided by S. What is the amplitude ratio? Amplitude ratio is Kp divided by omega. Phase angle is minus 90 degree, isn't it? That means your Nyquist plot should start on the imaginary axis making an angle of minus 90. That's why your Nyquist plot is starting only on this axis and it's getting terminated at 0 here when omega tends to 0. Okay. Correct? Similarly, when you are looking at the proportional controller, the transfer function is just Kc. What is the amplitude ratio for proportional controller? Kc. And phase angle is 0. Isn't it? So you can see that you get just a dot in case of proportional controller. I have again not mentioned here. You can see that this is the imaginary axis, is the real axis. Okay. I have not mentioned here. Is it clear? The interesting case is for PI controller, PD controller and PID. In PI controller, the transfer function is Kc into 1 plus 1 upon tau is. What is the amplitude ratio? Amplitude ratio is Kc into under root of 1 plus 1 upon omega tau I whole square. Isn't it? So when omega tends to 0, you get a Nyquist plot of omega tends to 0, then you get infinite, isn't it? And when omega tends to infinite, you get 0, isn't it? So in this case, phase angle. If you look at the phase angle, what will be the AR by Kc will be 1 when omega tends to infinity. This will be 0, so AR by Kc will be 1 when omega tends to infinity. Okay. So phase angle will start from minus 90 and it will approach to a value of 0. Isn't it? So that's why your Nyquist plot in this case is starting from here, which is minus 90 and which is making an angle of 0 when omega tends to infinity. PD controller will be reverse of that. So it is starting from 1, isn't it? And approaching to a value of infinite and making an angle of 0 initially and then making an angle of plus 90. And PID controller will be a combination of these two, isn't it? You can see it is starting from minus infinity going to a plus infinity, isn't it? Phase angle is starting from minus 90 and going to a plus 90. Correct? PID controller. So Nyquist plot is clear to everyone? Okay. Now let's move to another important topic, which is designing a feedback control system using the frequency response. In fact, whatever we have seen in last 4 classes is primarily to reach this point. So whatever we have seen, Bode plots, Nyquist plot, frequency response, how we can get amplitude ratio and phase angle, that was only to create a base so that we can go here. We wanted to design the controller. We wanted to see the stability of the control system using the frequency response. Reason is when whenever your transfer function is associated with a date time, you can find out the stability of the control system using a frequency response without approximation. Okay. Okay. Now this is thought experiment, slightly interesting. Let's say you are having a first order. Process. What will be the transfer function? Kp divided by tau ps plus 1. Isn't it? What will be the phase angle when omega tends to infinity? Minus. Isn't it? Now in this particular case, let's say the first order process is associated with a date time, and date time here is e raised to the power minus 0.1 s, and the process is kc e raised to the power minus 0.1 s divided by 0.5 s plus 1. Okay, proportional controller we are using. For a time being, let's assume that Gf and Gm is just 1. We have neglected the dynamics of the final control unit and measurement. Okay. Now in this particular case, I wanted to find out the frequency. Please hear me out. This is interesting. Otherwise, you will lose. I wanted to find out a frequency which will give me a complete phase reversal of the output. Please hear me out carefully. I wanted to find out a frequency for which your output is completely opposite of the phase with respect to your AC. So there is a complete phase reversal. That means what? Phase angle will be what? Minus 1. Phase angle is minus 1. So I wanted to find out the frequency at which my phase angle will be minus 1. Okay, how I can find out? This is the transfer function I have obtained. This is the open loop transfer function. Let's say I have opened the control loop just before here, measurement unit. Okay, so open loop transfer function will be GC, GP, GF, GF. That will be the open loop transfer function. Now this open loop transfer function will be given by this equation. What will be the phase angle for this equation? Tan inverse of minus omega tau p, that is the phase angle corresponding to the first order process. So tan inverse of minus 0.5 omega, that will be the phase angle corresponding to the first order process. And also there is a phase angle corresponding to this exponential term, which is a date time. So what is the phase angle of the date time? Minus omega t. There is no tan inverse in omega. Minus omega t. So we will have a phase angle by using this equation. Phase angle phi is given as tan inverse of minus 0.5 omega minus 0.1 omega. Now I wanted to find out this value of omega for which this phi phase angle becomes minus phi or minus 1. Okay. If I do the calculation, I will find out that this omega comes out to be around 17 radian per minute. 17 radian per minute. So if I am using the frequency omega equals to 17 radian per minute, अरे भाई क्या हो गया? कहीं कुछ पहाड़ गिर गया है? भूकंप आया है कहीं? क्या हो गया? किसी कोई कोर्स का कोई क्विज सबमिट कर रहा है, तो फिर वो लैपटॉप को बंद करो और ध्यान दो. ठीक है भाई, इतने देर से देख रहा हूँ भाई, कुछ हो गया होगा. पहले 2-3 बार मैं निगलेक्ट कर रहा था, पर वो रुक ही नहीं रहा है. और तुम लोग पीछे क्यों बैठे हो? आओ सामने बैठो. पीछे के दोनों आओ सामने बैठो. आप पीछे बैठ के मटर गश्ती करते बैठे. आगे बैठो. अरे अटेंडेंस हो जाएगा यार, मैं खुद मार्क्स कर दूंगा तुम्हारे अटेंडेंस. आओ सामने आओ. चलो. So now let's concentrate. We have only limited time. Okay. So we can find out the frequency omega for which my phase angle becomes phi. तुम लोग को भी बोला है क्या स्पेशल इन्विटेशन चाहिए डायरेक्ट की तरफ? कभी आओगे? ऐसा कुछ हो तो बता दो, पहले मैं फिर लिखूंगा सर को. बच्चे मान नहीं रहे, इनको आपकी हैंड रिटन में चाहिए. ओके. The frequency corresponding to the phase angle of minus pi. The frequency corresponding to a phase angle of minus pi or minus 180 is referred as a crossover frequency. Remember what was the crossover frequency we have discussed earlier? Crossover frequency is the frequency when my roots of the characteristic equation are located on the imaginary axis. On an imaginary axis. We will connect to this point. We will connect. Right now it is not connected. Right now it is not connected. I am saying that this particular frequency omega, when my phase angle becomes minus 180 or pi, that particular frequency is nothing but a crossover frequency. Crossover frequency. Once we get this crossover frequency, I wanted to find out the Kc value. So amplitude ratio, what is the equation for amplitude ratio for a first order system? First order system is a date time. What is the amplitude ratio corresponding to a date time? Amplitude ratio for a date time. 1. And amplitude ratios are multiplied. So what will be the amplitude ratio for this entire function? 1 for the date time, and for a first order process, it is Kp divided by under root 1 plus tau p square omega square. So we will have a amplitude ratio for this entire equation same as a first order. Same as a first order. So that is what is written. Amplitude ratio will be given by Kc divided by under root 1 plus tau p square omega square. Now once we have obtained a omega CO, which is nothing but crossover frequency, I can put that crossover frequency in this equation, in this particular equation, and I can put this amplitude ratio equals to just 1, and I can find out the corresponding value of Kc. Please hear me out carefully. This is what the most important part is. I will first find out the crossover frequency. Once I have found out the crossover frequency, this crossover frequency I am going to put in the amplitude ratio expression, and I am going to find out the corresponding value of Kc, for which my AR becomes 1. My AR becomes 1. So if I put AR equals to 1 here, and this omega CO come from this earlier equation, I can back calculate what is the value of Kc. Okay. So the value of Kc, for which my amplitude ratio becomes 1 and the frequency phase angle becomes minus 180, that particular Kc is referred as ultimate controller gain, Ku. That is referred as ultimate controller gain, Ku. So I am going to find out Ku. Now why this Ku is important? This Ku is important because if you maintain the controller gain greater than this, your system is going to become unstable. We will prove this. We will prove this. I am only creating the story first. We will prove this mathematically. Why I am saying this? So when you have Ku, which is nothing but the ultimate controller gain, when the controller gain is greater than this value Ku, your system is going to become unstable. Unstable. Okay. So what I am saying here is when my frequency is such that my phase angle becomes minus 180 and my amplitude ratio is more than 1, then my system is unstable. And this is what is referred as a Bode stability criteria. What Bode stability criteria is? When my phase angle is minus 180 and my amplitude ratio is more than 1, then my system is unstable. Now let's prove it mathematically and also with a simple thought experiment here. Then you will appreciate why I am saying this. Take the same example. Okay. Same example. I can find out what is the value of Kc corresponding to a amplitude ratio equals to 1 and omega CO equals to 17. Remember omega CO we have obtained here is 17 radians per minute. Okay. I can put this omega CO in this equation and I can put this AR equals to 1. I can back calculate Kc. That Kc comes up to 8.56. Isn't it? Now this is the point where my Kc value is 8.56. If I use a higher value of Kc, then I am looking at this another curve where Kc is greater. So now if I look at this particular frequency, if I track further, you will see that the corresponding 1. Corresponding amplitude ratio will be more than 1. Isn't it? Correct. Let's do a thought. This experiment is very interesting. Mathematically also we will prove. What is this experiment is? Let's say for the same process, there is a feedback control loop. There is a feedback control loop. The feedback control loop is like this. Okay. Initially, let's say I am giving a sinusoidal input to a set point. I am giving a sinusoidal input to a set point. So set point yft is given as sin omega t, and I am purposefully keeping this omega as 17 radians per minute. What is this omega here? It is a crossover frequency. Why I am keeping this crossover frequency? Because if I keep this crossover frequency in the input, my output will have a complete phase inverse. Okay, my output will have a complete phase inverse. For a time being, this entire loop I have opened here. Yes. Before the comparator, I have opened the loop. So this YM is not connected to the comparator. This input I have given, which is YSP, is given as sin 70t, isn't it? With that, what will be the open loop transfer function? Kc into e raised to the power 0.1s divided by 0.5s plus 1, isn't it? So for this open loop transfer function, my output Ym will be obtained by what? Sustained sine wave I am going to get, which will be minus sin omega t plus sin omega t plus phi. But phi in this case is minus 180. So what I am going to get? I am going to get minus sin 70t. Remember, when I am giving this input to this entire process, what will be Ym? Ym will be given by amplitude ratio into sin omega t plus phi. That is what we get output, isn't it? But here the phi is minus 180. So sin omega t plus 180 minus 180 will become minus sin 70. That's what we have. Okay, this is the output. Now again for a time being, once we have got this output, what we have done here is I have closed the loop. And I have converted this input equals to 0. So what will happen? Let's say I have closed this loop. Once I have obtained this output, I have closed the loop, and this input, which is YSP, which was earlier sin 70t, I have made it 0. What will happen? I got a sine wave here, minus sin 70t. Since there is a minus sign here, this will become plus sin 70t. And even though I have stopped giving the input, still this loop will continue. Why? Because once I have given this input here, this will become minus or minus, this will become sin 70t, this will act as a input here. Again I am going to get minus sin 70t, and this loop will continue. So I will get a sustained sine wave. Now the interesting question here is, if let's say my amplitude ratio is equal to 1, in that case what will happen? If the amplitude ratio is 1, in that case I will have a sustained sine wave with the same amplitude, isn't it? But if my amplitude ratio is less than 1, what will happen? This sine wave is there, but this sine wave is going to die out with time. And if my amplitude ratio is greater than 1, what will happen to the sine wave? It will grow with a higher amplitude ratio, isn't it? That means what? When amplitude ratio is more than 1 and phase angle is minus 180, my system becomes unstable. Correct? So that is what is the Bode stability criteria. Now it is clear to everyone? Is it clear to everyone? Yes, no? नहीं अभी नहीं समझ आया. मैथमेटिकली भी प्रूव करेंगे. ठीक है? How much time? 5 more minutes. Okay, let's prove it mathematically. So see, please note that this is the common mistake people do. When we have found out the stability of the control system system in a round stability criteria or in a root locus. What we have solved? We have solved 1 plus open loop transfer function equals to 0. When I am using this equation 1 plus G over TF is nothing but what? I am solving a closed loop. The point which I am trying to make here is when we look at the frequency response, we don't consider a closed loop. We find out the stability of the closed loop just by analyzing the open loop transfer. There's a difference. We find out the stability of the control system in a frequency response analyzing the open loop transfer function, not 1 plus G. We only look at G. We only look at G. This is the commonly asked question. In a frequency response, we find out the stability of the feedback control loop by analyzing only the open loop transfer. That is what we are doing. So see, this is the equation. This is the equation 1 plus G over TF equals to 0. I can take this one on the other side. G over TF will be equal to minus 1. Minus 1. Remember, we can find out the amplitude ratio and phase angle just by replacing S by J omega. Let's replace S by J omega here. So what I am going to get? I will have G over T of G omega C, and that will be equal to minus 1. Minus 1 is a real part. So what will be the amplitude ratio? Amplitude ratio is 1. What will be the phase angle? Imaginary tan inverse of imaginary part by real part. Imaginary part is 0 divided by minus 1. So minus infinity. Tan inverse of minus infinity. So tan inverse of 0 of, did I miss something? So in this case the phase angle comes out to be minus 180. So remember this Bode stability criteria is gives a phase angle of minus 180 and amplitude ratio of more than 1. There is some mathematical basis. It is not arbitrary. It is not arbitrary. In fact, this entire derivation is not there in any of the book. It is not there in any of the book. They will directly they assume that everybody knows. Okay. Alright. Okay, there is one more term. One more term we have to look at. So here you can see that when my phase angle is minus 180 and amplitude ratio is more than 1, then system is unstable. Then my system is unstable. Another way of representing the stability or Bode stability, Bode plots is by representing the amplitude ratio in terms of decimal. In some of the books, amplitude ratio is represented in decibels. What is decibel? Decibel is nothing but 20 log 10 AR. 20 log 10 AR. ठीक है? Okay. Before we look at this, there is an announcement. We have a quiz on this Sunday. Time is 2 to 4. Questions are tricky. I have made the question paper. Questions are easy, but you will not be able to do it. I will not find them anywhere. That also I can do actually. So the only thing I am asking you, please go through the material here. And the syllabus will be whatever we are doing today. Okay, for the quiz. Whatever we are doing today. I need 2 more classes. There are 2 tutorials remaining. I wanted to cover those tutorials and some of this material I have slightly gone through in a hurried manner. Maybe we can again revisit this one more time. Okay? So those things we are going to do it in the next week. So next week again Monday back, is it possible to do a tutorial on Wednesday, same time. Is possible Monday back, only Monday. Friday back we will have in the regular time. Online tutorial online. And nobody replies. मतलब ऐसा लगता है जैसे स्क्रीन से बात कर रहा हो कोई बात भी नहीं करता है पता भी नहीं चलता कि पढ़ रहे हो या नहीं पढ़ रहे हो that question mark is there. So online में we will have a tutorial for a Monday batch on Wednesday same time 2 to 3 same room. Okay. Another thing is I'm not sure whether we will be having a class टाइम है पूरा कौन सा टाइम कोई नहीं रिक्वायर हुआ ओके तो क्या करेंगे माइनस बट माइनस 1 वो आप